Okay, so let me. Ooh, I got two images of Samira. I got two of you on my end. It must be your twin. Okay.
I don't know
Uh,
how that.
that's okay. No problem. You get double the information. That's all I got to say. That's pretty cool. She's hacking us, guys. Watch out. All right. So let me continue with chapter 13. And we ended up on, I believe, slide 7 or 8. And I'm just going to back it up a little bit to tell you that this particular flow chart is very crucial with respect to this particular chapter and any type of calculations that we will be doing. The other thing um, is that remember how we talked about when we did the chapter on conversion factors from metric to English units. Uh, every factor there was a ratio that we can write that ratio one or two ways. Okay. And here, everything here that we worked our calculations with are ratios. The molar mass is a ratio. The molar mass has units of grams per mole. Okay. The mole ratio that's there in the center, well, that comes from the balanced chemical equation. And that's the stoichiometric relationship between maybe the two reactants, how many moles of each, 1 to 1, it could be 2 to 3, 1 to 4, whatever it took to balance that chemical reaction. All right. And then again, the molar mass is a ratio of grams per mole when we're trying to find the grams of what we're looking for. But the point is use this flow chart to help you get through these type of problems. Okay, so if you're given grams given, that is what the problem is giving you, grams of something, and you need to look and determine the grams of something else. And that's what we're talking about here, talking about grams fine. And so you got to go through this system right here. And it's all through moles. Moles is the central figure in these type of calculations because I cannot go directly from apples to oranges. And I use that analogy, apples to oranges, without a central common factor. And the common factor here is moles. Okay. Moles. You got to get it through moles to get from point A to point B. The other important factor is, remember, we talked about the molar mass. That is straightforward. You find the formula that you're working with, whatever it is, you put it together. We talked about putting, if it's an ionic compound, we put in ions first. Then we put it together to make the compound with the proper number of positive and negatives to make that compound. Once we got the correct formula, now we add it, we tally up the contribution that each atom brings to the compound, we tally up its atomic weight. So we count up how many of atom X, how many atom B, so on and so forth, add everything up from the atomic weights of the periodic table that we give you. Okay, use our periodic table, and that gives you the molar mass. Okay. And finally, the other important factor is mole ratio. That is the stoichiometric relationship between reactants or between reactant and products, or even between products themselves. Okay. But that is that coefficient in front of the balanced chemical equation that tells us how many moles of each they are relative to each other. And that's crucial. Then obviously this down here in the yellow boxes, this is only true when you are at STP. STP meaning 0 degrees Celsius and at 1 atmosphere. Okay, so if the question asks you to figure out a volume of anything and they don't tell you it is STP or list the temperature as 0 or 1 atmosphere, then there's nothing you can do with the calculations. You don't have enough information. Okay, you cannot calculate the volume of anything given the information you have unless you're told you're at STP. Then you can use this relationship that the volume of one gas, any gas, at at STP has a volume of 22.4 liters. Okay, now bear in mind I've been drawing the arrow in one direction, but you can start from down in the bottom right corner and work your way to the top left corner. Okay, or bottom left corner and work your way to the right corner. It doesn't make a difference. You can this kind of shows you how you can go from left to right, right to left. Okay, so study that flow chart. And when you work on the problem, have that flow chart there handy so you can see how you attacking the problem, how you working it, and how you moving from point A to point B. Okay. All right. So here we have this question that says, write and balance the reaction of hydrochloric acid and solid cobalt. Well, we have a reaction here that's only giving you the reactants. There's no products here. Okay. So you might think, well, wait a minute, how do I know? Well, this is what you do know, or you should know. There are only 6 types of reactions, chemical reactions that we have in chemistry. Okay, only 6 types. And by a process of elimination of those 6 types, we're going to determine what type of reaction this is. Okay. And once we know what type of reaction this is, then we can figure out what are our products. Okay. And I'll go through that here in a second. You know, yeah, I've been told a lot, yes, chemistry is complicated. There's no question about it. It is complicated, but so are other fields. There's a lot of complication, whatever field you do, whatever field you're in. But to overcome a problem, whatever field it is, a complicated one, you break it down in pieces. You break it down stepwise with what information you have, and little piece by piece, you put it together, and you are able to solve this big old complicated thing. Okay, and that's what we're gonna do here. All right. So let's write down what we do know about anything here, because we're given the reaction. 2 other things. They're telling you, for example, that cobalt, see the problem? Whoa, got the wrong. That's no good. Let me clear that up here. Too big. Okay, they're telling you something here. Cobalt will be in the +2 oxidation state as an ion. That's a hint. Okay, that's a hint here that might help us out. So keep that in mind. But the cobalt's reacting, and when it does react, it's going to be a +2. It's going to have a +2 charge. All right, so let's write down what we're given. So we got hydrochloric acid, HCl, aqueous. Okay, and or plus, because and converts to plus, solid cobalt. Okay, so that's what we're given, and that's it. So we don't know the products. Okay, well, we don't know them now, but we're going to figure it out. All right. Refresh your memory with respect to the 6 types of reactions. We did a lot of examples. First one type of reaction. Remember we talked about the combustion reaction? Okay. Well, what is a requirement of combustion reaction? Oxygen, right? Anytime you burn anything, you need oxygen. Is there anything here mentioned about oxygen? Nope. So we can eliminate that guy. That leaves us 5 reactions left to figure out. What's another type of reaction? Acid-base reaction. Remember acid and base, the hydroxide? Okay, neutralization reaction, remember that one? Okay, well, we got acid here. Yeah, we got acid or hydrochloric acid, but do we have a base? We have no hydroxide here. No. So acid-base reaction we can get rid of. So combustion reaction, acid-base reaction, we eliminate. Okay. What else do we have? Combination reaction. Remember the combination reaction? Where you put together A plus B to give us AB? Remember that? Well, normally A and B are elements. Well, we look at the reaction we're given. Cobalt obviously is an element, but hydrochloric acid is not an element. But we can eliminate combination reaction. Okay, so we got 3 so far. You got 6 to go. What was the opposite of the combination reaction? Well, we had a decomposition reaction. Well, a decomposition reaction is basically the opposite of a combination reaction, where you take a compound, you do something to it, and it breaks down. I got a question here in the chart. Give me a second here. Oh, okay. And Norma, you may be correct. An iPhone, wherever iPhone is, will be correct too. But let's go through it just to make sure we understand how we got to it if you did not recognize it immediately. Okay. So decomposition reaction, not an option 2, because we have 2 reactants and not 1 reactant. So that's 4. So we got that. Now, the other type was a double, what was it? Single replacement. Well, let's figure it out. Let's wait that let's settle that for last. But we have the double replacement, right? Remember the double replacement? I'm getting right here. For some reason my pen is acting up. A double replacement reaction. Okay, replacement. Now, if you recall in the double replacement reaction, you will always have 2 reactants, which we do here, but you will always have 2 reactions. The other aspect is you always have 2 reactants that are in the aqueous phase. Okay. And furthermore, they're going to be ionic compounds. We don't have only one of these is ionic, and that's hydrochloric acid. Cobalt's a solid. Okay. So double replacement reaction, we can eliminate. And so the only logical leftover reaction that you have to work with is a single replacement, which those of you who put that in chat is correct. But how do you verify that? Okay, how do we know that? Okay, well, because if you recall, in the single replacement reaction, I'm going to clean my mess up here in a minute. We had a metal in the elemental form, and then we had another metal in an ionic form. And basically, the metal in elemental form replaced the metal in ionic form to give you the AX plus B. Okay. Now, here we have a metal in ionic form, which is cobalt. But B, you might be confusing because B is a metal, but we don't have a metal here. We have hydrochloric acid. But it's got to be a single replacement reaction because it doesn't fit the properties of the other reactions. And then you remembered, when I go to the activity series of my, where'd it go? Give me a second here. Can't find my. I got a big mess here. When I go to, don't know why it's not showing. Bear with me. There we go. When I go to the activity series, okay, remember that all these metals that are reactive, it's a relative scale, and they're all relative to hydrogen. And the 2 forms, the ionic form of hydrogen is H+, okay? And obviously the elemental form of hydrogen is H2, the gas, right? So H plus. So going back to the reaction, you can see that HCl plus cobalt. Here is the ionic form of hydrogen in the H plus form coming from hydrochloric acid. We also look at the activity series and find that cobalt is more reactive than hydrogen. Okay, that's the first question you ask. Second question is this: is the most reactive metal slash hydrogen in ionic form? And the answer is no, because cobalt is not in an ionic form. Therefore, yes for a reaction. Yes, reaction. Okay, so we replace the cobalt with the hydrogen. Obviously, in doing that, hydrogen now goes back to the elemental form, and cobalt, as we were told, now is in the +2 state. But before we put it together, write them on the side in the ionic form before we put it together in the formula. And obviously, what the anion would be the chloride. So the chloride, we know it's a -1. It's a group 7 element. Okay, gains 1 electron, becomes chloride. So our formula says here that we're going to need 2 chlorides for every cobalt. So our formula is COCl2. Now, its physical state, obviously, HCl is aqueous, cobalt is solid, hydrogen is a gas. What do we know about cobalt chloride? Cobalt 2 chloride, okay? We know that all chlorides on the solubility table are soluble, okay? And it's aqueous, that is correct, Samara. So it's aqueous because it's soluble based on the solubility table. Now we have the reaction. Okay, now we know the products. Now we wrote down the reactants, we wrote down the products. Now we got to do is balance it. Okay. And you can do this a number of ways. The simplest way is recognize 2 Cls on a reactant product side. So if I simply put a 2 in front of hydrochloric acid, that balances my Cls, which picks up my hydrogens to 2, which are balanced by default because hydrogen's diatomic. We got 2 hydrogens on the right. And so we have a balanced chemical equation, okay? And we did this stepwise because we didn't know, I got HCl and I got solid cobalt. I can give them the formulas. I know that. This part is given to me in the problem, so I can write that down. This part, I had no idea. So I had to break it down and figure out, well, what are my products? Okay. Now I can sit there and memorize this if you want, because there's like millions of chemical reactions you can memorize, but you don't have to do that. If you go through what you know, we talked about 6 chemical reactions, and you go through those 6 and realize what you don't have, eventually you're going to end up with, you got one that this reaction must be. And the other aspect too, another way to remember is that I have a metal reacting with an acid, and it by default will react for those metals up to lead and the activity series. Acid, any type of acid, will react for those metals starting with magnesium on the activity series up to lead. Okay. After that, copper and silver and mercury, those metals after hydrogen, they require a lot more stronger acids and combination of acids to react. Okay. And so, yes, it's another way to look at it. I got an acid reacting with the metal, it is going to react. Those metals that are underscored, sodium up to lithium up to sodium, those are bright. Those react with water all by themselves quickly. They don't need acid. The water, the moment water hits it, you generate the metal hydroxide automatically and hydrogen gas. Okay, so we got the product, figure out the reactants. Now we can move on to bigger and better things here. Let me clear my mess up. Okay, so we write the reaction and we have it balanced. And now the reaction tells us we have 2 hydrochloric acids are required for every 1 cobalt atom or molecule or mole to give us cobalt 2 chloride and hydrogen gas, and everything's balanced. We're good to go. Now we can do any type of problem that they ask us now. Okay. So the first one tells you, how many liters of gas at STP will form if 5 grams of cobalt reacts? Okay. Well, a couple bits of information that you should know is one, the question says, how many liters of gas? So obviously they must be talking about hydrogen, right? It has to be, because the cobalt 2 chloride is not a gas. It's a ionic compound that's soluble in water. So we're talking about hydrogen. And then they say, if you took 5 grams of cobalt and reacted. So we're talking about 5 grams of cobalt. So 5 grams of cobalt, how many liters am I going to make? So I put that down myself so I can keep track of where I'm going, what I'm doing. Okay. That means that I can ignore all the other guys because I'm not concerned about them. Because the question's not asking about cobalt 2 chloride or hydrochloric acid. It is between cobalt and the gas, hydrogen gas. Now, I also look and see at my stoichiometric relationship, it's a 1-to-1, 1 cobalt to 1 hydrogen gas, that mole ratio. Okay, so I got it all set up. Now I know what I need to do. I write down what I'm given. Okay. I'm given 5.00 grams of cobalt. And I don't have it here, but I should also note that I also, for my sake, I also write down that eventually I'm going to have something equal, some factors equal to liters of H2. And I write that down because that tells me whether I'm going in the right direction as far as setting up my conversion factors. Okay. So I write down what I'm given. I write down where I got to go. And then I find a way to get there using the conversion factors that I'm given. Also, the other information that's important and keep in mind is they tell you you are STP. Okay, being STP, which is is 0 degrees Celsius in 1 atmosphere. Okay, they either will say STP or they may give you the temperature 0 degrees in 1 atmosphere. That infers that is at STP. So under those conditions, I know that 1 mole of gas would occupy 22.4 liters per mole. So I got a conversion factor here that I may need to use, but it's available. I have a question, 22 exactly. And that's liters per mole. Don't forget the full units. It's not, that's a summary, that's good. It's 22.4 liters. Don't forget, it's liters per mole. It's a ratio. Okay. So now I got everything I need. I can start working through the problem. Keeping in mind that I'm in grams, no matter where I go, no matter what I do, I need to convert to moles first. I cannot go from point A to point B, apples to oranges, without starting with moles. So the very first conversion factor I have is my atomic weight of cobalt that will convert that 5 grams of cobalt to moles of cobalt. Okay. And notice here that I'm dividing when I start with grams. When I divide by the atomic weight or molar mass to give me moles. Okay. So at this point, the calculation would give me moles of cobalt. keeping track of my units. Now, if you don't see it, remember any whole number, any number by just simply putting a line and a 1 underneath puts it into a ratio. And that helps you to see it better. So that 5 grams of cobalt cancel with grams of cobalt. Unit wise, at this point, is moles of cobalt. Okay, I'm not too worried about the math with right now. I'm just working through the units. My next unit is where do I need to go? I need to get to hydrogen. Okay, so I need to convert. I need a factor that converts it from moles of cobalt to moles of hydrogen. And that comes from the balanced chemical equation and the stoichiometric relationship. Because they're from the balanced chemical equation, 1 mole of hydrogen is equivalent to 1 mole of cobalt. That's the ratio, 1 to 1. And again, keeping track of my units as I progress with my setup, notice that my moles of cobalt are canceling out, leaving me at this point. And if I were to stop the calculation with moles of hydrogen gas, but I can't stop it. I got to go one more because the question asks for liters. And keeping in mind that you are at STP allows me now to use that ratio of 22.4 liters per mole with liters in the numerator. And so that's where that goes. Okay. And as I progress, I'm keeping track of my units. I've done none of the math yet. I'm just setting my units up to my factors up. So I know now that unit wise, I'm at liters, and that is where I need to be because based on the question. Now the math is on you. Okay. So you take the math, get your calculator, plug in the numbers, and you could end up with almost 1.90. Let me clean my mess up here a little bit. There you go. Okay. But all the along, I'm keeping my units, checking them, making sure they're set up properly and that they're canceling out, leaving me with the units of liters, which is what the question asks for in the first place. And like I stated, the math is on you. Now, this type of problem, for example, maybe it's worth 5 points, okay? I'm going to restate this here. The answer itself could be worth 1 point. And then this whole setup right here could be worth 4 points. Okay. So therefore, if you report an answer and it's correct and all you show was 1.90 liters, well, congratulations, you got the right answer. And I'll give you 1 point. Okay. But you didn't show your work, especially if it says show your work. If it doesn't say show your work, you give me the answer, you're good to go. No problem. You get the full 5 points. But if it says show your work, this is what we're talking about. Okay. Show your work clearly and how you did it, how you set it up. And if, for example, you make a mistake and you type in the wrong number and you do a calculation and you say, you know, you have an answer of, I don't know, 200 liters, for example, for whatever reason. Well, obviously, you know, you won't get that point, but guess what? You will get 4 points because you did set it up. I would not take points away because you gave me a wrong answer. You won't get that 1 point. I give you points because you did set it up properly. Okay. Okay. So keep that in mind when you're answering these questions. Now, it's best if you can show your work and just like that so I can follow you. Sometimes you put numbers up there. I'm not following some of these numbers here. Now, it is feasible, if you recognize it, to combine these 3 factors into 1 unit. And if you recognize that and you show me the units, I don't have a problem with that. It shows me that you recognize that and you can make 1 unit out of that and present that as your work, and that's fine too. All right. But until such time you're not sure, put them all out there like we just did. Okay, so now we got a second question. This one says, if you have 2.374 liters of hydrogen gas formed how many grams of hydrochloric acid reacted? Okay. And so here they're telling you that the reaction already happened and it was measured, the amount of hydrogen measured came out to be 2.374 liters. They want to know how many grams in grams, how many grams of hydrochloric acid reacted to give us 2.374 liters of hydrogen gas. Okay. So we're only concerned about HCl and H2. Cobalt and cobalt 2 chloride, not in the picture. Okay. So what do? As always, we write down what we're given. Okay. And in my case, because I want to know, keep track of where I'm going, I need to go to grams of HCl. And that just, I write that down. So just keep me honest there, and it keeps me going in the right direction as far as setting up my problems. Now, obviously, once you do a number of these, you don't have to do all the steps I'm talking about. I'm going stepwise to show you how to attack these problems. It's like solving an algebra problem. When you first learn algebra, they tell you put a negative A over here, negative A on this side, and you do that until such point you recognize the numbers. You don't have to do any of that because you recognize what you're doing, okay? And you go right to the answer. But anyway, here we go. First step, obviously, we are at STP. We have 2.374 liters of hydrogen gas. We need to convert that to moles. Like I stated, we got to get to moles. Regardless if you start with liters or grams, we got to get to moles. And we use that conversion factor because we are at STP. If that STP was missing, you could not answer the question because you don't have enough information. Okay, so the question is not answerable because it's not STP. So that one gives us moles of hydrogen gas, and then the center conversion factor gets us to moles of hydrochloric acid. Okay, moles of hydrochloric acid. Keeping track of my units as I go along. I got moles canceling out here. I'm good to go. Then, once at this point I'm at moles of hydrochloric acid, I need to get to grams. So I need the molar mass of hydrochloric acid. And we get that by simply adding up the atomic weights of all the atoms. I got one chloride, one hydrogen. That gives us a total molar mass of 36.46 grams per mole. That is the molar mass of hydrochloric acid. Okay. And then also, as always, just to keep me in the straight here, that I'm going in the right direction, moles of HCl cancel. Guess what? I'm in units of grams of hydrochloric acid, which is what the question asked me to do. So now I plug in the numbers into the calculator, and lo and behold, I got an answer. And let me clear the mess out there. 7.72 grams of hydrochloric acid. Okay. All right, here's another one. Another word problem. Got to convert it to an equation. Okay. Now, this is an interesting one. Unlike some of the ones being given, like the previous one, we had to determine what the products were. This one gives you the answer, it gives you the products, okay? But it gives it to you in letters and words, and you need to convert that to a chemical formula. All right. So let's do this. We have HCl gas. So we're starting off with HCl gas. Okay, so obviously we're not in the aqueous systems. This would be called hydrochloride, hydrogen chloride, because it's in the gas form. And if it's an aqueous, HCl is called hydrochloric acid. Okay. All right, so HCl in the gas form plus obviously is the plus symbol, oxygen gas. Okay, oxygen gas, its oxygen, as we know, is diatomic, and so it's O2. Produces, tells me, the arrow. Okay, chlorine gas. Notice chlorine, not chloride, chlorine. So that's also one of the diatomic gases, Cl2 gas, and water vapor. Hopefully you know that water, its form is H2O. Okay. Vapor tells you that it also is a gas. Okay. So we got that. Now we got to balance it. Okay, we got the formula. We got two chlorines over here on the right. Maybe if I put a 2 in front of HCl, yes, that balances my CLs, but that kicks up my hydrochloric acid, right? My hydrogens. So what if I put I got 2 already, so my hydrogens are okay. However, I got 2 oxygens in the left and only 1 on the right. So what if I put a 2 here that kicks up, that gives me 2 hydrogens, but it kicks up let me restate that. It gives me 2 oxygens, but it kicks up my hydrogens up to 4. Okay, so that means maybe if I change my 2 here to 4, that balances my hydrogens, right? But then what happens? Now I got 4 CLs. Well, I need a 2 in front of chlorine gas. Wow, okay, let's find out if I'm balanced now. Okay, I got 4 hydrogens on the reactant side, 4 on the product side. 4 chlorides in the reactants, 4 CLs in the products. 2 oxygens as oxygen, 2 oxygens as water. Guess what? We're balanced. Notice what happened there? Okay. Let me let's start that one more time. I think it's noted to be shown again. Okay. Okay, so I kept it simple now. You can do you can do this any number of ways, but for me, the simplest way is just go with like we just did. I put 2 in front of HCl. Why? Because I had 2 CLs as products. Okay, so that looked okay. I got 2 hydrogens as reactants. Now I got 2 hydrogens as water. So those are good, okay, at that time. Then I go back and check my oxygens. Well, I got 2 over here, but I only got 1 as water. Okay, so I could put a 2 here. That kicks up my oxygens where it should be, but same time that kicks up my hydrogens to 4. So what I do, I get rid of my 2 and put a 4 in HCl. Okay, that brings up my hydrogens, but guess what? That kicked up my chlorides to 4 now. Okay, and then I go back to products. I put a 2 of chlorine, and now I'm balanced. Okay, so it's a matter of going back and forth. You try your first number. That first number you try maybe have to be up later on. Okay, and now we go back. We did a double check. Everybody's happy. Everybody's balanced, and we got the reaction. All right, so Question says, how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? So how many liters of chlorine can be formed if 3 liters of oxygen react completely at STP? So we got 3 liters here. We want to know how many liters here. Okay. So we're only concerned about those two. As always, what do we write down? Oh, the other aspect is obviously we are at STP. So that's important because we can use that 22.4 liters per mole. Okay, don't forget that's the ratio. Somebody had a question. Liters per mole. There you go, Samara, you got it. All right, so we write down what we're given. That's 3 liters of O2. We are at STP, so we can use our factor there to get us out of liters into moles. Okay. And then from the balanced chemical equation, it's a ratio of 2 chlorines to 1 oxygen, 2 to 1. So at this point, now we are in moles of chlorine. Being in moles of chlorine now and being STP, we put that conversion factor back, and that kicks us back to liters of chlorine. Okay. And that ends up to be 6.00 liters per chlorine. Now, notice something of how that system, how the work was set up. Do you notice something there that you can simplify this calculation? You notice that this 22.4 cancels that. Okay. And so I don't really need that, right? But that is only the case, and I repeat, let me clear it up a little bit here. That is only the case of when everybody is in the gas phase. Gas, 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 and gas. And especially the two that you're calculating have to be in the gas. That we know that these two are going to cancel out by default. So all we need is the stoichiometric relationship between the two that we're calculating from, the oxygen and the chlorine. Okay. But until you're comfortable with that, continue to set it up the way we set it up until you can recognize that and you're comfortable with it. Okay. And so you can see here the liters cancel, moles cancel, leaving us liters of gas at the end. Until such time that you're comfortable with that, you can see that I can eliminate this one and this one, okay? And moles cancel, and my unit-wise, I'm still left with liters, okay? All right, hopefully you can recognize that. But if not, don't worry about it. Work it through systematically, step by step, until you get more comfortable with it. All right, now try these at home. And then this is good if you can't work it through. This is good for bringing in on Tuesday. We can work it through. Carbon reacts with oxygen gas to form carbon monoxide. Okay. So how many liters of carbon monoxide at STP can be made if you start off with 15 grams of carbon in the first question? Second question, same thing. How many liters of carbon monoxide at STP can be made from 20 liters of oxygen gas present? Okay. Try that out. You should come up with 28 liters of carbon monoxide for number 1 and 40 liters for carbon monoxide number 2. Okay. And if you don't get it, bring it in on Tuesday and we'll go over it, figure it out. That's a typical type of questions you'll find, homework and exams and activities, things like that. So kind of overview. All right. What we've done is we've taken the elements, and we have been for a while now, and made compounds out of them. Okay, there's 118 elements. We're not using all those 118. You notice chemistry, we're kind of limited to what we're working with. Okay, we don't use all of them. So we're taking the elements. From the elements, we make compounds. Now, these compounds could be either ionic or they could be covalent. Ionic meaning that obviously it's a combination of a metal and a non-metal, and covalent meaning that is a combination of non-metals. Okay. Now, from that compounds, we have compounds reacting with compounds or elements or something. We got reactions. From those reactions, we get products, obviously, and then we balance these reactions. Balancing these reactions gives us the stoichiometric ratios that we need to do the calculations. Okay. And so we can do calculations of reactants and or products or any combination thereof based on these ratios, which come from the balanced chemical equation. And we can give answers in terms of moles, grams, or even in liters, and only if we are at STP. Okay. This flow chart, you really need to use it and be familiar with it, because this will help you through these type of calculations, telling you what you're given, what you're trying to find. Okay. And remember that the ones in yellow are only true if you are at STP. So use that. That helps you quite a bit. That, ladies and gentlemen, brings us to an end of chapter 13. And what I want to do is just go through one more example from your worksheet. Now you might be wondering what worksheet, right? Okay, where is my worksheet? Hold on, I can't find mine. Okay, I found it. Now, on the course website, if you recall, and I also got them on the modules in there, there are worksheets that I'm hope you use and utilize and use them and work them through. They do have the answers, but don't look at the answers. Work through the problems, okay? Work through the problems and see if you can answer the question. And I just thought that was interesting here because this is something, you know, you're all familiar about alcohol. And in the first example here, they give you, it's called fermentation. And it's a complex chemical reaction, you know, of, you know, not just making wine, but making all beer and regular alcohol, you know, whiskey and so forth, of converting glucose, which is a sugar. And what it does, it converts it into ethanol and carbon dioxide. So some of you may be at home, you may have a home brew or a home beer kit. Maybe you make your own wine at home or you make your own beer. You know, you might see bubbling going on, and that's what's observing here. You got a chemical reaction that you're creating carbon dioxide, okay? And so here's a general structure of glucose. Glucose is its general formula, and they give you the general formula here, and not giving the full structure because it's a whole area of organic chemistry where you got to learn certain things here. But basically, glucose is made up of 6 carbons, 12 hydrogens, and 6 oxygens. Now, the interesting property about glucose, in fact, all sugars, is they are a class of compounds called alcohols. They themselves are alcohols. In fact, they're polyalcohols. Now, you'll find here, and it says here, C2H5OH. Well, that is the general formula for ethanol. Now, it's kind of misleading here because all this time we've been talking about the polyatomic ion OH, and we think of that as a hydroxide, but this is not that hydroxide ion. Structurally speaking, I'm just going to draw it out. Carbon has this, let me change the color here. Carbon right here, if I look at the structure of carbon, I have carbon, and then what's bonded to the first carbon I put down are 3 hydrogens, just like we've been doing before. You got a single bond. But carbon then is bonded to another carbon. That's the second carbon. That's why there's 2. And that carbon has bonded to it 2 hydrogens. But then we also have bonded to it this OH group. This is what we call alcohol group. Now, these are not organic ionic compounds. These are organic compounds. Nothing but carbon and hydrogen. They're not hydrocarbons because they have other things other than carbon and hydrogen. They have oxygen. So they're just organic compounds. They're covalent. And what denotes an alcohol is this OH group, which we do call a hydroxide group. This is side note information for right now. So that's what makes it an alcohol, this OH group. Now, the structure of glucose is they have hydroxy groups too. Hydroxy groups, they're an alcohol. A lot of your carbohydrates are alcohols. But the triglycerides and stuff, when they break down, they eventually make a 3-hydroxy group, 3 groups, an alcohol group. Anyway, this is ethanol. You might be familiar with the term methanol. Methanol, if you're brewing this alcohol at home, you got to be a little bit careful. Okay, methanol has 1 carbon, hence the term, the prefix meth. Okay, 1 carbon, 3 hydrogens are bonded. Then it also has this OH group, makes it an alcohol. This is methanol. It's also known as a wood alcohol. Now, this is ethanol. Hold on, I'm having trouble with my pen. Hold on there. Ethanol has two carbons, hence the prefix F. And then some of you may be familiar with rubbing alcohol. Isopropyl alcohol is another common name they call it, but the correct scientific name is 2-propanol. 2-propanol. Pro means 3 carbons, and then there's 2 types. There's the 1-propanol, but that's rubbing alcohol. All of them have in common the OH group, the alcohol. Well, back to the fermentation. If you don't fermentate correctly, you create methanol or wood alcohol. And if you drink that wood alcohol, it can cause blindness. Okay, so you gotta be very, very careful. Blindness. So a little side note there on your alcohols. And there's butanol, and there's all just a whole bunch of different compounds that are all alcohol. All right, so let's go back to the problem. So we're given this problem here where we got glucose, which is a polyalcohol, okay, reacts in the process to form ethanol and carbon dioxide. So first things first, I realize that I'm going to need atomic weights. So I'm going to very quickly, I already recalculated them. Where's my pen? There you go. Oh, here we go. So molar masses, this one is 180.18 grams per mole for the glucose, okay? For the ethanol, I get, what do I get for ethanol? 46.08 grams per mole. And maybe if I need carbon dioxide, that would be, what did I say? Carbon 32 and 12, that'd be about 44 grams per mole. Okay, so I'm putting the atomic weights of all these because I may need them. All right. All right. So the first question it's asking you is this. Calculate the mass of ethanol produced if I start off with 500 grams of glucose. All right, so I'm starting off with 500 grams of glucose. I need to know how much alcohol in mass in grams of ethanol. So I'm only concerned about glucose and ethanol. Don't care about carbon dioxide. Okay. And in this question. And so obviously, as we've been doing, I want 5 grams. I'm starting off with 5 grams of glucose, and I'm just going to label that G. Okay, glucose. Okay. And I need to go to how many grams of ethanol. Now, I put that down as ETOH. That's the general shorthand way of writing ethanol. So ET is the eth, and the OH shows it's an alcohol. Okay. And so the first thing I need to know is, like I've been doing all along, we've been doing, is we need to convert the grams of glucose to moles of glucose. So moles of G is on top. And the atomic weight of 180.18 grams of G is in the denominator. Okay. The grams of G cancel out. Okay. That would give me moles of G. Well, I need to get to moles of ethanol, and I use the stoichiometric relationship from the balanced chemical equation that 2 ETO ethanol per 1 G. Okay. Okay. 1 G, 1 mole of G. So that you can see how moles of G cancel, leaving me now unit-wise with moles of ethanol. And then I need one more factor. I need grams of ethanol, ETOH, per 1 mole of ethanol. Okay. And that is the molar mass, 46.08. Checking my units, ethanol cancels. I do all those numbers. I think I did do this calculation. What's my number that I come up with is, where do you go? Of course, when I'm looking for my number, I wrote it down and I can't find it. Oh, okay. My number is, you might check your math, my math. Make sure my pen, right? I come up with 255.7 grams. Okay. 255.7 grams. So think about it. If you took 500 grams of glucose and you put the material to fermentate that glucose, you make some strong moonshine. 255.7 grams of ethanol. Okay. That's quite a bit of ethanol, really. All right. And you probably have to do a distillation. That's what they do when you hear, like in moonshine, you distill it, you heat it up, run into a condenser and collect it in another container. And you have your pure alcohol. So you'd be like 100, 200 proof alcohol. Yeah, 100%. But it won't be 100% long because ethanol has a propensity of absorbing moisture from the atmosphere. And after you've made it, and if you don't protect it from the atmosphere, it picks up the moisture. It gets down to about 95%. Yeah, that's pretty standard, somewhere in that ballpark. Anyway, so that's how to calculate this problem. No different than what we've been doing, okay? The reactants are different, the products are different. And this is true whether I do 500 grams or I do 500 tons of glucose. to make a whole bunch of alcohol. The same reaction occurs, the same stoichiometric relationship is observed. Okay. So work through the worksheets. They'll give you additional information. Okay. Clear this up. I'm going to stop it at this point here. All right. And like I stated, let me